Example 4.1, displacement under dynamic loading. A cool side story for this is back when I was an undergrad, before that I was an industrial mechanic, and I went into a bolt shop, a place to buy hardware, industrial supplies, and I was talking to the gentleman behind the desk, and I needed a bolt. He asked me how much weight I needed to hold. I said a number, and he asked if it was dynamic or static, and I said, why would it matter? And he said, well, your dynamic loading is twice your static loading. And I was like, well, how would he know that? And then years later, I was taking a vibrations class, and I saw the math for it, and I was like, oh, that's really fascinating. So if you get nothing else out of this example, know that the dynamic loading on a force is twice that of your static loading. And now we can walk through some of the math to get there. So let's assume that we have a dump truck, right? And this is a dump truck from the Armed Forces of the United States in Operation Prime Beef. It was a training operation in the 80s, but it's a publicly available figure, and I like the name of the operation. So a load of dirt M is dumped into the back of the truck, right? So that's what we're doing here. We're dumping dirt into the back of the truck. And the truck bed can be modeled as a spring mass system, right? So just a spring and a mass, no damper. Where the dirt is loaded is F of T equals mg, right? So we've got mass and gravity is applied to the system. So how does the maximum displacement of the truck bed compare to the steady state displacement of the truck bed with the dirt in it? So, all right, so setting up the load, right, of the truck, let's just say is 1 unit, right? Let's just set the load of the dirt as 1 unit. We have a load that's going to be a step function, right? And it's a step function because we don't have dirt in the truck, and then we're going to have dirt in the truck at the end. So we can obtain a steady state system, a transient and steady state displacement of the truck bed, knowing the undamped displacement, right? So our undamped displacement of that system is going to be x of t is equal to 1 over k 1 minus cosine of omega nt. I'm going to close out in slightly bigger brackets. And if I want to put that into the units I had before, I'm going to say that is equal to mass times gravity over k of 1 minus the cosine of omega n t. Oh, I need a bracket, and I need a slightly bigger bracket. Okay, so if I think about this, when do I get the maximum displacement on this structure? Cosine can only be a maximum of +1 and minus and -1, right? Those are going to be my maximum. And I've got 1 minus cosine. So when my cosine is 1, I'm going to have a displacement of 0, which isn't very maximum. And when my cosine is 2, I'm going to have a displacement. Sorry, when my cosine is -1, I'm going to have a displacement of 2. So I can set when the cosine of omega t is equal to -1, I get max displacement. So if I just write that out here, I'm going to get x of t for my step response is equal to mass gravity over k of 1 minus -1 is equal to, we can just say x of max is equal to 2 mg over k. So if you are designing a truck, right, or kind of any dynamic system subject to a step response, your displacement, your max displacement, is twice your static displacement. It's a good rule of thumb, right? Can you model a dump truck as a 1 degree of freedom system? As someone who teaches vibrations, I would say you can model anything as a 1 degree of freedom system. Is it a useful model, right? All models are wrong, some models are useful. But in a 1 degree of freedom system, your dynamic response to a system is always twice your static response. It's in an engineering sense, it's a very good rule of thumb.